Welcome to Dr. Ernest Simo's series on satellite communications. This tape presents the fundamentals of VSAT networks. Within the last 20 years, the cost trends of satellite communication systems have experienced a sharp decline, while their applications, performance levels, and reliability standards have increased significantly. As a result, satellite communications technology presents one of the most cost-effective options for the delivery of data, voice, and video in today's telecommunications environment. Recently, a class of satellite technology known as Very Small Aperture Terminals, or VSAT, has emerged as a leading candidate for use by corporate networks. As the name implies, VSAT technology is characterized by the small antennas utilized throughout the network. These small remote stations are typically connected in a star configuration to a central station referred to as the hub. The hub is a large, very expensive facility and represents the heart of the network. It incorporates all the network management, network communications, network operations, and network control capabilities. Up to now, the high cost of the hub station, which can be as high as $1 to $3 million, places a fully dedicated VSAT network out of the reach of most organizations. However, new creative financing strategies and service offerings, such as the sharing of satellite channels and hub facilities, can now allow small and medium-sized users to realize the full benefits of VSAT networks with minimal and, in some cases, no initial capital investment. Let's review, examine, and explain some technical and functional aspects of VSAT networks. Let's talk about characteristics of very small aperture terminal networks, their technology, the regulatory environment, and some typical VSAT network applications. The broadcast capabilities of satellite communications technology allow VSAT networks to offer point-to-multipoint distribution services. VSAT technology is also suitable for multi-point-to-point concentration requirements. In such configurations, tens, hundreds, even thousands of remote terminals are connected via satellite to a central location. Such a central location may be the corporation's headquarters, a database, or a data processing facility. A unique attribute of VSAT technology is its ability to provide mobile communications over wide geographical areas. Multi-drop lines, microwaves, and optical fiber systems don't have this capability, and therefore cannot be used to implement non-permanent telecommunications facilities, which can support such applications as news gathering, live coverage of special and sporting events. Rapid implementation of new communications links can be critical in some applications. VSAT technology can provide communications opportunities where none existed before. Once the system parameters have been determined, a VSAT link can be implemented virtually overnight. This is in sharp contrast to terrestrial leased lines, where delays and waiting time of 6 to 9 months can be experienced for the installation of 9.6 to 56 kilobit per second lines. Satellite technology is uniquely characterized by its high penetration power. In satellite systems, the spacecraft defines the service area known as footprint. Within this area, all locations, including those with difficult access, isolated and sparsely populated regions, have communications capabilities. In a VSAT network, the satellite, an ultimate broadcasting tower, can provide international, domestic, rural, or intercity communications. In some cases, technical, regulatory, and economic arguments can be made for intracity VSAT communications links. The flexibility of VSAT technology allows quick response to changes in network topology and network reconfiguration. For networks which often need to accommodate new users, easy expansion can be achieved by simply adding a VSAT station at a new user's location. In other words, VSAT networks are highly flexible with respect to the addition, relocation, or deletion of sites. Another major feature of VSAT networks is security against single-point failure. A typical microwave link is designed to carry hundreds of voice-equivalent circuits. So any failure at a repeater may result in the loss of hundreds of circuits. In optical fiber systems, the loss is even more significant, since long-distance fiber systems are designed to support thousands of voice-equivalent circuits. By contrast, VSAT networks are cost-effectively designed for thin route, point-to-multipoint applications. As such, the failure of any remote terminal doesn't affect the rest of the network. One may ask, what about the satellite's transponder? After all, a satellite can be viewed as a repeater in the sky. Well, the answer to this question can be projected from past experience. Once in operation, satellite transponders have proven extremely reliable. The lifetime of spacecrafts is limited by the fuel required to maintain and control the satellite, rather than by the failure of the communications electronics. The third element of a VSAT system, the network hub, is generally designed with necessary redundancy arrangements and space diversity strategies to protect the network against potential catastrophic failure. Satellite communications are routinely designed to deliver high-quality data transmission and typical bit error rates, or BER, better than 10 to minus 7. This means that for every block of 10 million bits or pieces of information transmitted through the system, only one bit is likely to be detected as an error. By contrast, multi-drop lines typically operate with a bit error rate of 10 to minus 5. This is approximately 100 times inferior to the transmission quality of satellite-based systems. Using VSAT technology, existing nodes of data communications can be replaced at cost savings. In terrestrial communication systems, the transmission cost per circuit is strongly dependent on distance. Consider microwave systems. The implementation of a microwave link involves not only the electronics, but several repeater facilities and sometimes very expensive towers. Now consider optical fiber systems. A fiber link also includes electronics and repeater stations. The right-of-way and installation costs are distance dependent and can be very high, especially in built-up areas. By contrast, the circuit cost is insensitive of distance in satellite networks. So, by using state-of-the-art satellite technology, significant reductions on the user's telecommunications expenditures can be realized. Advances in satellite communications technology during the late 70s and early 80s have been responsible for low-cost VSAT networks. These are the major issues that have stimulated the emergence of VSAT technology. The availability of Ku-band satellites with high receiver sensitivity and radiated power translates into a simple and cheap ground segment. Lower power, smaller antennas, or less sensitive receivers are required from the ground in order to achieve the same performance as larger Earth stations operating in conjunction with lower-powered satellites. Major developments in solid-state technology have enabled the mass production of more reliable ground terminal electronics at low cost. These devices include solid-state power amplifiers, SSPAs, and high-power converters, HPCs, with power output ranging from 1 to 10 watts. And low-noise converters, LNCs, with noise temperatures ranging approximately from 80 to 250 degrees Kelvin. The gain of parabolic antennas is directly proportional to the square of the frequency and the square of the antenna diameter. So, the gain of a given antenna remains approximately constant if the antenna size is reduced by a factor of 2 while the frequency is doubled. Hence, higher frequencies translate into higher antenna gain if other parameters affecting the gain remain unchanged. For a given set of system performance requirements, the use of Ku-band, therefore, allows significant reduction in antenna size relative to C-band. Like a conventional satellite system, a VSAT network consists of a space segment and a ground segment. The ground segment components include the very small aperture terminals and the hub station. The communication path from the microterminal to the hub station is referred to as the inbound link. Conversely, the path from the hub to the microterminals is known as the outbound link.